First thing, you just have to launch Vivado. This will take 2 minutes. This is very slow. Okay, this is faster this time. Okay, so first thing is you're going to create a project, and we go next, and I'll name this as VLSI Basics. Okay, next, and this is a RTL project, Register Transfer Logic. Say next. And here you can add sources, but you can add them later, but make sure target language is VHDL, simulator language is mixed, right? And then say next. And constraints also you can add later, so we just skip that. Say next. Now you have to choose a device. So what we are using is a general purpose FPGA from RTX 7 family, and this has 324 pins, so it says CSG 324. This is a ball grid array, 324 pins, and the speed grade is the slowest one, -1. So we are going to use 100,000 CLBs. So this is the XC7A. XC7A means it's a RTX family, 7 RTX 7 family. 100,000 T means there are 100,000 CLBs. CSG is a package type. It's a ball grid array. 324 pins, so it is 18 rows and 18 columns. Okay, so we'll choose this one. Another thing is it doesn't have GTX transceivers. Usually it has 6 GTX transceivers for high speed data acquisition. Okay, so we don't have that. So next, and just say finish. Okay. So once this is done, the project summary is over here. It just says what is the path. It just says about device and things like that. Okay. So what is important is project manager. So all the activity which includes entering a design source to running simulation to doing synthesis, then implementing the design, and then generating a bit stream and then downloading it to hardware. So everything is managed from project manager, right? So the first thing is we are going to add sources. So right click on design sources and say add sources. Under add or create design sources, just say next, and here you can say create file, and here you can name the file. So we are going to do a half L. Correct? So just click OK, and we are not going to use the default library. We are going to name the library as subcomponent. Correct? So you have to remember this library name because you are going to use this a number of times. So library is subcomponents. Say finish. So once you hit finish, now this is a wizard which will create the basic template for the code. Code is when the statements are concurrent, it is called code. When the statements are sequential, it is called a program. Right. So it has two parts. One is the entity, that is the architecture. Entity is the outline. Architecture is the functionality. So I will give architecture name as HA. So now I have to specify input ports. So there are two input pins. One is A, other is B, and then there are two output pins, sum and carry. Correct? Now this one is the direction, or what is called the mode. So you can see that there is input mode, there is output mode, then there is a in-out mode. In-out mode is used usually when there is a buffer. So there is another mode which is called buffer, but is in synthesizable VHDL that is not there. Okay, so we use a output mode here for these two things and say OK. So once you do that, this should appear under design sources. Okay, so that's it. So now you can double click it, open it, and anything which is double dash is gray colored, that's a comment. And comment ends with the carriage return. So I can type my own comment. So this is basically a half header. So I can say this is a half header. Once I have done that, I'll remove all other comments. I'm ready to write the code. Okay, so this part is the entity, and there is only one line inside it that says port A comma B is mode in of type std logic. Now std logic is a data type which is defined in a library called IEEE and in a package called std underscore logic underscore 1164. Right? So it means that you have to specify the library at the top and which package of library you are going to use. You have to specify that. And dot all says that everything which is in the package has to be included. Okay. So once you are done with this, now the code knows that std underscore logic is a data type. So A and B are the input signals. So it says mode in, and it is of type std underscore logic. Correct? And some comma carry is mode out, and the type is std underscore logic. Note that keyword is entity followed by the name of the entity is again keyword, port keyword, bracket open. Then you write the all the ports which are of same type. In this case, it is A and B. This is mode in, and the type of the data type which is std underscore logic. Similarly, you have some comma out as mode out std underscore logic, and then note that you will put first the bracket, so the last entry doesn't require a semicolon. Semicolon comes after the bracket. Okay, so every statement in VHDL ends with a semicolon. Right now, and half header. And is a keyword. Half header is the name, and then semicolon. So this is an entity which outlines the component. So it just tells what are the input ports and what are the output ports. Architecture, HA is the name of the architecture of this entity is, and then this section between architecture and begin, this is called declarative section. So all the signals which you are going to use as intermediate signals can be defined here. You cannot define signals anywhere other than here. Okay, and then begin, and whatever is between begin and end is called the body section of this architecture, where you can write concurrent statements. Sequential statements are not allowed in here, only concurrent statements. And then you can also do instantiation of subcomponents. Only two kinds of statements can be there inside the architecture. Correct? So in this case, we will simply do sum is assigned. So assigned is less than equal to A XOR B. So basically says sum is A XOR B. So this is a behavioral description of sum of a half header. So what it tells is XOR A with B and then assign it to sum. Now this is a concurrent statement. It's not a sequential statement. It does not matter in which sequence it has been written. Okay, the statements are going to execute based on events. If there is an event on A or there is an event on B or both, then this statement will execute. So this would be evaluated right inside expression, but it will not be immediately assigned to sum. It will be assigned after a delay which is set by the simulator, which is called a delta delay. So this statement is called a behavioral statement. It is also called a data flow statement because it is showing a flow of data between inputs and outputs. Okay, and remember that this assigned is less than equal to, it is not equal to, because this creates a driver for a signal called sum. So signals are basically wires, variables are storage locations. So here we are dealing with signals. So these ports are signals. The ports are a type of signals which have a mode defined, input or output mode. Okay, so sum is assigned. So that means that the output mode signal or output mode port will always be LHS, and then the input mode ports will always be RHS. If you do reverse, it will not work. Okay, so now you can say carry is assigned A and with B. So that completes the code. Okay, so this code, if it is incorrect, you will see red lines. For example, let's say you forget this semicolon. It should come up and say that there is an error. So I don't know, it doesn't come up. Okay, we will see this later. Okay, so this is a complete program. You can just save it from here. Click save. So once it is saved, you can go ahead and run the simulations. So if you hit run simulation, then behavioral simulation is going to simulate that. Simulation. Okay, so what it is doing is it is doing something called elaborate stack. So what it is doing is your behavioral description is replaced by gates. Okay, so these gates are primitives which are inbuilt. So that's what it is doing. So let's see. So here it comes with unresolved. U stands for unresolved. Okay, so we can just say restart. Okay, so you can just say restart. So the first step is gone. So basically now we can specify the values of various input signals and observe the output signals. So to do that, we are going to use this panel called objects. Correct? Under objects, if you right click on A, you can say force constant, and you can give it a hex value, let's say 0. And then B, I can give another hex value. Okay, I can give another hex value, say 0. So both inputs are 0. I'm not going to assign the output ports. The input ports are going to be assigned, right? So after that, if I look at the top, there is a toolbar here which says play for the specified time. So I've set the specified time as 100 nanoseconds. So you set it as 100 nanoseconds. Okay, so you have this as 100 nanoseconds. You just say run for 100 nanoseconds, and that's your answer. So if your A and B are 0, sum and carry are 0 0. Correct? Now what you can do is you can right click on anything you want to change. So in this case I want to change A to 1. So I can just force a constant 1 on it and then hit run for 100 nanoseconds again. So now you see A is 1, B is 0, sum is 1 and carry is 0. If you want, you can use view all. So there is a zoom fit. So when you do zoom fit, you are going to see the entire stack. Okay, the first input, second input. Okay. Okay. You can size these windows to see more area. So for example, you can size this window like this, and then you can say zoom fit. Zoom fit. Okay, now I'm going to put another 2 more inputs. So this is going to be 1 and this is going to be 0, and I'm going to run for another 100 nanoseconds. So I can say that I still have a sum of 1 and carry of 0. Now I'll put 1 1 1 1, and here I again do this and I see sum is 0, carry is 1. I will do view all. So you have all the 4 states. So do all the 4 states. You have to do here assignment. Okay, and so view all. Okay. So you have 3 states. You have to do 4 states. So you have all the input states. So you have verified this. Now, if you want, you can save it. I'm just going to close it. Okay, so I don't want to see the simulation. I can go to File and say Close Simulation and say OK. So I have verified in simulation that this thing works. Now, if you remember that running the simulation, it did something called elaborate design. So now, if you want to look at schematic, you can double click to schematic under RTL analysis in Project Manager. So you just double click it and just accept to what it is saying. Don't worry about a lot of warnings it comes up. Just click schematic and the RTA. Okay, it is trying to initialize the device, so don't worry about this step. Okay, so that's our schematic, correct? So A and B is carry, A XOR B is sum. Okay. So this is the elaborated design. So now what I'm going to do is I'm going to run synthesis. Okay. So just click on run synthesis. So it'll show over here on the right top what it is doing. So it hasn't started synthesis. So now it's saying running synthesis. Right? Just say okay and just let it run. Okay, so once it has run synthesis, you can look at the synthesized design. Just say open synthesized design, say okay. And it will say want to close the elaborated design, say yes. Okay, so it doesn't make sense here, a lot of this stuff, don't worry. Okay, what I'm interested in is I have done the design, but I haven't mapped the logical pins with the physical pins of FPGA. So this part is called defining the constraints or IO constraints. So for that, what you have to do is you have to go under Windows IO ports. Once you click that, you know that there are two scalar ports as inputs and two scalar ports as outputs. Now you have to refer to the data sheet of the FPGA to map the physical pins, or if you have the board, like for example, we are going to use Nexys4 DDR. In this case, I'm going to use two pins as input and two LEDs as output. So these pins are L, so I'll dictate L16, and then you can say the other pin is going to be J50. J50. So A is L16 and B is J50. Type here L16, capital L, and J50. Okay, so similarly for LEDs, I will say K15 is the carry LED and X17 is the sum LED. Okay, so once this is done, we have to also specify what kind of voltage levels we are going to work with. Now on this Nexys4 DDR, there are three voltage levels available. One is 3.3, which is for all the peripherals, in this case LEDs and switches. So I'm going to set this as LV CMOS 33, which stands for 3.3 volts. I do this for all the scalar ports. Okay, so once I have done this, right, I have to save this constraint file. Okay, so the other voltages on this board are 1.8 volts, which is required to run the FPGA, and 1.25 volts, which is required to run DDR2 memory. Okay, fine. So we are going to go to file and going to say save constraints, and one project can have only one constraint file. So if you do a new design, you would have to delete the previous constraint file before you specify the new constraint file. So one project can at a time can have only one constraint file. Okay, so let's say I'm going to give this as a test HA, so which stands for test half header, and say okay. Okay, so constraints are saved. Now I have to synthesize this design again because the synthesis is out of date, because I have specified logical pins map to physical pins. So I have to synthesize this again. So run synthesis again. Okay. Okay, so once it is done, you have to just go and click run implementation and say okay. Now, if you dismiss this dialog box, you can also run implementation from the project manager, right? So you can use a project manager and go under implementation and say run implementation, or you can run the implementation from here itself. So once you do that, now the design is taking the physical shape. Up till now it has been just a logical design using gates. Now what it is doing is it is mapping lookup tables, mux, and flip-flops if required to a circuit. There are no gates in FPGA. Only lookup tables, flip-flops, and multiplexers. Well, there may be gates inside them, but it is not visible to you how they are implemented. So what it's doing is it did a place and route between various LUTs, muxes, and flip-flops using the buses inside this FPGA and switching matrix. It is optimizing the design, which means that it is placing them in a smaller section closer to the IO pins. So once this is done, I'll show you what this is. Okay, so once it says that it has implemented it, you can say open implemented design. Okay, this step is optional. It is just for you to see a implemented design. Okay, you so let this finish and I'll show you. That's routing the design. Okay, so I can open the implemented design. And what I can show you is the implementation is over here. So I'll just zoom in to this section, and what it will be just one lookup table. So if you see, this is a CLB and it is just using one lookup table. Okay, and you can zoom out, fit all. You can also see which pins it is using. So if you see here, okay, so this saying that H17 is one of the pins which is used, right? And J, so K15 is another pin used, J15 is another pin used, right? So this routing information is also there in connection to this. So once this is done, you can go here and say generate bit stream. So after implementation, you will generate a bit stream. Okay. So the programming is very simple. You have a USB port. So what it has is a JTAG port to USB. It's a micro USB on the board. You have to just hook it up to your USB of the computer. And once it is hooked up, if you switch it on, it will show you built-in self-test. This is built-in self-test. It's testing all the LEDs and all the switches, so you can see if these switches are working, right? So these switches are working, right? And on this board there is a FPGA, there is a DDR2 for larger programs. Okay, then there are two 4 segments 7 segment displays, right? So you can display total of 8 digits. Then there are 16 switches on Nexys4 DDR, and there are 16 LEDs on top of it, right? And then there are two tricolor LEDs which you can change the color by giving a different intensity to each LED. And this is a power LED, and this is when the programming gets done, this one lights up. Okay, so there is another one which is busy and then it lights up. Okay. So once you are done, you can click open hardware manager. Okay, and once you are done with this, you can say open target auto connect. And once you are done with this, you can say program device and say program. Once this is done, the done LED just shows that this is done. So now 00 gives you 00, and this gives you carry as 0, sum as 1. Again carry as 0, sum as 1, and now sum is 0 and carry is 1. Okay, so now this basically completes it. Now before you switch off this FPGA board, switch the power off, you have to go here and say close hardware manager, say OK. Okay, so once it is done, now you can switch it off. Okay. So this basically completes the introductory part. So you can just close the implemented design and it will come back to just one file which you have written. Okay, so this is the end of the first